Hi, and welcome to the video on practice problem 9. So you'll notice that in questions 1 through 5, for all of those questions, you are provided with the chemical structures of the molecules. Questions 6 through 7, you are provided with chemical formulas of the molecules involved in the reaction. So what you'll need to do for those questions, for questions 6 to 7, is actually draw the Lewis dot structure. Question 9 and 10 add on an additional challenge as well to that, in that instead of providing you with a chemical formula like you would typically see with these problems, what they provide you with is simply a description of the reaction. So in addition to having to draw the chemical structure from the chemical formula, you also need to figure out your complete balanced chemical reaction. Okay, so I'm going to model question 9, which is the hardest. And then don't forget, for these problems, for questions 2 through 5, since I modeled number 1 for you, you need to pick 3 from 2 through 5 to do and show me your work, either by taking a picture or typing your equations into the document directly. And then for questions 6, 7, 8, since I'm modeling 9, you won't do 9, and 10, so 6, 7, 8, and 10, then what you'll do is you'll pick 2 of those problems, so 2 of the harder types of problems, and show me your work for that. Okay, so I'm going to model 9 for you because it is the hardest. All right, so in this one it says combustion of methane. So again, not a lot of information here. So the first thing I need to do is write down the reaction for the combustion of methane, and then I'll balance it. Now remember, combustion reactions involve burning something in oxygen. So combustion for all combustion reactions will always react with oxygen. O2 will be your reactant. And what are the 2 products for the combustion of a hydrocarbon or an organic molecule? Remember, if it goes to completion, the 2 products are carbon dioxide and water. So just to recap for this first step here, you have to read, it says combustion of methane. You need to know, if it's a combustion, then one of my reactant will be O2. And then for organic molecules, the products would be CO2 and H2O. Now we're going to go ahead and balance it. So we do our tally. I have 1 carbon, 4 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 2 plus 1, so 3 oxygens. Now remember the strategy for balancing combustion reactions. We balance the oxygens last, and that strategy is because oxygen is found in 2 molecules on the same side. So on the product side, oxygen is found in CO2 and H2O, so we balance any element found in 2 or more molecules last. So we balance the oxygens last. So let's focus on the hydrogens. I have 4 on the reactant side, 2 on the product side. To get them to balance, I'm going to change the coefficient in front of H2O from the invisible 1 to now a 2. That gives me 4 hydrogens. And now let's carefully count the oxygens. 2 plus 2 for the 2 waters, total of 4 oxygens. Okay, so my carbons and hydrogens are looking good. Let's look at our options. I have 2 on the reactant side, 4 on the product side. That's an easy fix. So put a 2 in the front there. Okay, so now what we have here is just the balanced chemical equation. Now we're going to go and we need to draw the Lewis dot structures to figure out what types of bonds we have in the molecule. So remember, Lewis dot structures, that's what it helps us for. So the steps for Lewis dot structures: 1, you count the total number of valence electrons, and you get that from the periodic table. Remember that in your periodic table, group 1 has 1 valence electron, group 2 has 2 valence electrons, and valence electrons are the electrons in the outermost shell. We skip the transition metals. Group 3 has 13, group 14 has 4, 5, 6, 7, and then last is 8. Okay, so carbon, bringing in group 14, it has 4 valence electrons, and hydrogen being group 1, it has 1 each. So that means CH4 has a total of 8 valence electrons. All right, now that I have my total number of valence electrons, we're going to make our skeletal structure. And to do that, you choose your central atom, and then and that will usually be the one that's the least electronegative. It's typically the one that's written first. So I think the easiest to do is just to use the one that's written first, but there are two sort of other things you look for. It's the least electronegative atom except for hydrogen, because hydrogen can only form one bond, so it can't go in the middle. Or it's the one with the most unpaired electrons in its valence shell. So we're going to pick the central, and in this case it's going to be carbon, since again the hydrogens here can't go in the middle. And then attach everything to it with a single bond. So we got 4 hydrogens, we're going to attach those on with a single bond. And then we check the structure to give everything an octet. Now in this case, we've used up, we had 8 electrons, 8 valence electrons, we used them up, 2, 4, 6, 8. So the structure is good, and the carbon, which has its octet, has 8 electrons surrounding it. Hydrogens, of course, they only have what's called a duet, so they're good. So this is our structure. Let's do the same thing for oxygen. So oxygen O2 is in group 16, so it has 6 valence electrons. And that means this oxygen molecule is a total of 12. So since there's no central atom here, there's only 2 atoms. You just connect the 2 atoms with a single bond. This is our skeletal structure. I've used up 2 electrons to make this. It means I have 10 remaining. So a couple of strategies. One thing you can do is you can figure out with the 10 electrons, sort of preview whether or not you're going to form a double bond. And the way that you do that is you figure out how many electrons does each of the atoms need to get an octet. Each oxygen needs 6 more electrons around it to get an octet, since each already have a pair through this bond. That would mean in total this molecule needs 12, but I only have 10 remaining. So I have less than I need to give everyone an octet with this single bond. So that tells me I'm going to have a multiple bond here. And since I'm only short 2, that would just be a double bond. The other way of doing it is you take your 10 electrons and you just arrange them around. So 2, 4, 6. I'm going to put 4 more here. You just arrange them around the molecule, and you'll notice that this oxygen does not have an octet, but this one does. So what does that mean? Well, they're going to have to do some extra sharing. So I'm going to take a lone pair and move it there, and then I get this as my structure for oxygen. Okay. All right, so now I have the structure for O2, I have CH4. All right, now let's do CO2, so the same thing. Carbon is in group 14, has 4 valence electrons, and oxygen has 6 each, and there are 2 of them. So that means my total number of valence electrons here would be 16. So I pick my central atom. In this case, it's the carbon. It's the least electronegative element. And again, it's usually the one written first anyway, so that's usually very helpful. Put that in the middle. Make my skeletal structure by tacking on my oxygens to the central atom with a single bond. All right, I've used up 4, so that means I have a total of 12 left. But to give everything an octet, each oxygen would need 6, and the carbon would need 4. So I have a lot less than I actually need. So that means that's my clue that I'm going to have to do some multiple bonding there. So we're going to add the 12 remaining to our terminal atoms. So put the 12 on the terminal atoms. Okay, and now to get the carbon in octet, I can take some electrons from there, some electrons from there. All right, and so that's my Lewis dot structure for CO2. Now everything has an octet. This carbon has 2, 4, 6, 8 electrons around it. This oxygen has 2, 4, 6, 8 electrons around it, and so does that one. Okay, so I've got my Lewis dot structures there. Okay, last one I used to do is for water. Same thing, hydrogen. Each hydrogen has 1 valence electron since it's in group 1. Oxygen has 6 valence electrons since it's in group 16. And I'm going to put oxygen in the center. Remember, you can't put hydrogen in the center because it can only form one bond. Tackle my hydrogens. So I had a total of 8 valence electrons here. I used 2 up to make, 4 to make these 2 bonds, and the oxygen needs the last 4 to give it an octet. Okay. So what I've done so far is just write my balanced chemical equation and then drew the structures for my reactants and products so I can figure out what type of bonds I have. Now, by the way, you don't need the lone pairs as you're doing this. It actually, you don't need it to get the bond information because you just need to know the types of bond between the atoms. But this is what the Lewis dot structure process looks like. Final thing. I'm going to clean this up and rewrite this. So before we calculate the change in enthalpy for this reaction, one thing to consider or to remember to do is to make sure you bring down the coefficients from the balanced chemical equation so that you know how many of each type of bond you have. So in the case of CH4, there's a coefficient of 1 there, so I can just leave that as a 1. Oxygens, I have 2 of those, so I'll have to put the 2 there. CO2, there's 1 of those, and then water, there are 2, so I put 2 there. Okay, so now I have the information to go ahead and solve this, and I'll show you what this answer looks like so you can sort of see. This is the hard part. So what does it look like when we finally finish solving it? Here we go. Here's our change in enthalpy for the reactants calculated out. I have 4 CH single bonds, oxygen-oxygen double bond, and I get that as a total. On the product side, I have 2 carbon-oxygen double bonds and 4 hydrogen-oxygen single bonds. I add that together, and then I subtract the 2 values, and I get negative 710, and this is also exothermic because delta H is less than 0. All right, so you've seen the process. I hope you found this video helpful. Have a quality day.